Good morning, beautiful people. طيب أنا سلمى سيد IGCSE chemistry teacher I'm starting this initiative to help out the students who are panicking في الفترة اللي احنا فيها دي أو struggling with their studies. Every online module is free access. If you know someone who would benefit from this, please pass it forward. Okay, without further ado, this specific module is about topic 8 in your syllabus, which is acids, bases, and salts. What I always advise my students to do is the first thing to check the big picture. Okay, so this is a basic zoom out at a topic 8. It's divided into four chunks. The first chunk tackles the basic definitions of acids and bases, the term concentration and strength. What do we mean by indicators and what are the different color changes and the various reactions of acids and bases. In the second chunk, we're going to see four different types of oxides. Acidic in the basic if you're in the core syllabus. In the extended syllabus, it's going to extend into neutral and amphoteric as well, depending on the position of this element in the periodic table. In the third chunk, it's all about preparing salts using three different methods, basically depending on whether the salt I'm preparing is soluble or insoluble. And finally, the fun part, all about lab work. This is the qualitative testing or identification. So I have a certain unknown compound and I'd like to know which cation or anion does it have. Or I'm conducting a certain experiment in the lab and I need to identify the gas being given off. So this was basically the big picture. Now let's zoom in into the details. Okay, starting with the first chunk, the term acid refers to a substance with a pH below 7. It usually has a sour taste and it's corrosive. By corrosive, we mean it burns the skin. That's why when dealing with acids and alkalis in the lab, you should wear gloves as a safety precaution. Type. An acid is defined actually as a proton donor. And what do we mean by proton? This is the positive or the hydrogen ions. So what difference does HCl have with ethanoic acid? HCl is considered a strong acid, similar to nitric acid and sulfuric acid. Why is that? Because in water it will completely get dissociated into hydrogen ions and chloride ions. So it provides a great deal or a high concentration of hydrogen ions. Whereas if I have ethanoic acid, this is an organic acid which is actually weak, it will only partially ionize in water, giving less concentration of hydrogen ions. Okay. An acid would typically react with one of three substances. Acids react with metals to give salt and hydrogen. So this is the general equation. However, if the examiner specifies a certain acid and a certain metal, you need to specify the products as well. So let's say I'm dealing with HCl and magnesium. So the salt is expected to be magnesium chloride plus hydrogen. Of course, this is not balanced, so we need to insert the coefficient 2 here. Alright, now it's important to note here that not all metals can react with acids. They have to be above hydrogen in their activity series. So, in the case of copper, for instance, silver, or gold, they will not react with acids. So if I have HCl plus copper, no reaction. An important skill in your IG paper is to identify the observations in a reaction. If I have a reaction giving off a gas, in this case hydrogen, I'm expected to see bubbles. So when the question is asking you about observations, I shouldn't be writing the name of the product. This is not something I see or smell. I should say effervescence, fizzing, or bubbles. So with the case of copper, again, the observation would be no change or no bubbles. The second reaction of acids would be with bases, and bases that we're going to see shortly, it's a compound that has hydroxides or oxides in it. So the reaction between them is known as neutralization, which is mostly an exothermic reaction, meaning it gives off heat, and the products would be salt and water. Let's also use an example here. If I had HCl and sodium hydroxide, my salt would be sodium chloride and water. Again, if you're in the extended syllabus, the balanced chemical equation is required. For the core syllabus or pre-IG students, the examiners would usually ask you about the word equations instead, or simple chemical balancing, or simple balancing of chemical equations. All right, now how did I identify the salt here? Basically, the salt, it's the result of reacting an acid and a base. It's the product upon the reaction, where the metal ion comes from the base and the anion part, in this case chloride, comes from the acid. Meaning, if my acid was hydrochloric acid, my salt is expected to be a chloride salt. If it's a nitric acid, it will give off nitrate. If it's sulfuric acid, it gives off sulfate, and so on. Alright, now, and finally, the third reaction of acids is with carbonates. And when acids react with carbonates, they give off salt, carbon dioxide, and water. Let's give an example for that. Nitric acid plus sodium carbonate would give me sodium nitrate, carbon dioxide, and water. Okay. In the beginning of my explanation, I mentioned something about strong versus weak acids. And to remind you, we said strong acids like hydrochloric acid or nitric acid, for instance, completely ionize in water to produce a great deal of hydrogen ions. Weak acids instead are partially ionized. So when I represent that, we use an arrow for the ionization of strong acids, whereas the reversible sign or the equilibrium sign in the case of weak acids. Students often mistake strength with concentration. This is something you need to pay attention for. Now, concentration basically means how much acid is dissolved in water. So let's say, for instance, I can prepare a concentrated sample of hydrochloric acid and a dilute sample of hydrochloric acid. Does this mean that the hydrochloric acid is a weak acid? No. Hydrochloric acid is already classified as a strong acid, and this is shown by the pH. You already know that the pH scale lies from 0 to 14, 7 being neutral. Below 7, it's an acid. Now, the strong acids have pH from 0 till 2, weaker acids from 3 till 6. So HCl does have a low pH, okay, typically 1 or 2. If I'm having a dilute sample, this means the ratio of HCl to water is basically more acid. If I'm having a dilute sample, this means I have little amount of the acid compared to water. مخفف, in other words. Whereas the concentrated sample means we have greater quantity of acid compared to water while comparing the same volumes. On the other hand, ethanoic acid is a weak acid, and I can still prepare dilute or concentrated samples of that. Now, done with the acids, moving on to the bases. You've already heard that to identify this example as a base, it needs to have the hydroxide ions, and the base has the ability to accept protons from the acids. That's why they react together in a neutralization reaction. So whereas acids are proton donors, bases are actually proton acceptors. And in water, they will dissociate or ionize to produce the hydroxide ions. Now, similar to acids, we have weak and strong bases. Weak bases would have pH between 8 till almost 11, whereas from pH 12 till 14, these are the strong bases. Alright, so in bases we also have got the strong bases like sodium hydroxide, potassium hydroxide, the most famous examples. Weak bases would rather be ammonium hydroxide, also known as aqueous ammonium type. We have something important in the lab known as indicators. What are indicators? These are used to give us a certain color change, thus indicating whether the sample is acidic, basic, or neutral. And you need to know the color changes with most commonly the litmus paper. So the litmus paper turns red in cases of acids, blue with alkalis. We have another indicator known as the methyl orange. The methyl orange is actually red with acids, whereas yellow with bases. We have another indicator known as the phenolphthalein. It's colorless in acids, but pink or purple with the alkalis. And another indicator would be the universal indicator, which actually gives us the rainbow colors. So basically red, orange, yellow in case of acids, green in case of neutral solutions, something like water with a pH 7, blue in case of bases, and finally violet if I have a strong base. So blue with a weak base and violet with a strong base. If you've realized, the litmus paper gives me the red color with any acid, whether for instance a strong acid like HCl or a weak acid like ethanoic acid. So it doesn't differentiate between the pH, it just indicates whether it's an acid or not. Whereas something like the universal indicator, since it gives me a spectrum of colors, it is more reliable or more suitable to identify the strength of the acidity or alkalinity as well. Alright, so back to the case of the bases. We already said that the bases react with acids in a neutralization reaction, and these are basically oxides, hydroxides, or carbonates. The typical reactions would be, first one already covered, the second, which is usually forgotten by students, I don't know why. Bases typically react with ammonium salts. Upon heating this, I'll produce a salt, water, and a very important product here is ammonia. Ammonia gas, it's the only alkaline gas, so basically it's going to turn litmus paper blue. It has a pungent smell, ريحته نفاذة معروفة. And this reaction, you usually get asked about it indirectly. So let's say if I'm having a reaction with an ammonium salt and I expose to it a base, the ammonia given off can be tested using a litmus paper turns blue. You will relate this to a later topic in the syllabus, which is the air and water. And sulfur and carbonates type. Later on in the syllabus, you figured out that copper, or basically calcium oxide, calcium hydroxide, and calcium carbonate are all suitable substances to use to neutralize the soil acidity. In the meantime, something like ammonium nitrate or ammonium hydroxide, this is a suitable fertilizer for the soil since it's a source of nitrogen. You know that fertilizers need to supply the plants with a source of nitrogen, phosphorus, or potassium, or a combination of all of them or two of them. So basically, the first one, calcium oxide, commonly called lime or quicklime, is suitable to neutralize the soil acidity, whereas ammonium nitrate is a fertilizer. However, it is not recommended to add them together at the same time. This is because of this reaction. Simply because I'm going to lose my fertilizer in the form of ammonia. So the nitrogen that I've provided the soil in the form of ammonium nitrate is going to be lost as ammonia. Hence loss of the fertilizer. Right, so these are the colors of the universal indicator we referred to earlier. And this is the part where we tackled the different indicators and the different indicator colors. So as a recap, litmus is red in acids, blue in bases, but it doesn't differentiate between a strong or a weak acid and base. The methyl orange is red in acids, yellow in alkalis or bases. Phenolphthalein is colorless in acids, but pink in bases. And by the way, speaking of alkalis, when you hear the term alkali, this is actually a soluble base. So this means that not all bases are soluble in water. Only the soluble ones are the ones referred to as alkalis. And the most soluble, or the most common, actually, the most famous alkalis are sodium hydroxide, potassium hydroxide. Whereas something like calcium hydroxide, for instance, this is slightly soluble. Something like copper oxide, copper hydroxide, this is insoluble. Now let's relate this to real life. What is the importance of controlling the acidity? I've mentioned earlier that farmers tend to add something like calcium oxide or calcium hydroxide, calcium carbonate, which are lime, slaked lime, and limestone respectively to the soil. Why is this important? And this is usually a 2-mark question in papers 3 or 4. Type. We need to do that in order to neutralize the soil acidity, which is important for the crop growth and yield. Why? Basically, plants cannot grow too well if the soil is either too acidic or too alkaline, so we need to adjust the pH. So the first mark goes to saying that if the examiner is asking about the importance of lime, for instance, this is needed to neutralize the soil acidity. Why is that? The second mark is to improve the crop growth or yield. Now, done with the first chunk, moving on to the second chunk, which are the types of oxides. Type. We have 4 types of oxides. Again, if you are in the extended syllabus, basic oxides, the first type, are formed from a metal. So for instance, if I'm dealing with sodium oxide or sodium hydroxide, copper oxide, copper hydroxide, these are basic oxides. And since they act as bases, this means that if I add them to acids, a reaction actually occur forming salt and water. However, they are not going to react with bases. And their pH should be high, above 7, again, since they're bases. On the other hand, acidic oxides are actually formed from nonmetals, which are found on the right side, of the periodic table. Metals being on the right, metals being on the left, nonmetals being on the right. Acidic oxides like sulfur dioxide, carbon dioxide, these tend to have a low pH below 7, and they're going to react with bases to form salts and water. So again, if I try to add HCl, for instance, to sulfur dioxide, I won't observe anything because no reaction will occur. Now, amphoteric oxides tend to behave as both, as acids and bases. So, something like zinc oxide or aluminum oxide can react with acids and bases. Whereas neutral oxides like water, nitrogen monoxide, carbon monoxide, notice here that carbon monoxide, CO, is neutral, whereas carbon dioxide was acidic, a common trap. So neutral oxides, as the name suggests, they're not going to react with either acids or bases. Now, a typical question here in your exam would be, how can I test if my sample is, let's say, basic or amphoteric? So what I'm gonna do is simply, I'm gonna try to add a named acid and a named alkali. When you see this in the mark scheme, it means that you have to give an example. So let's say to your sample, I will add HCl and sodium hydroxide in a test tube separately. If it reacted with only acids, then it's a basic oxide, but if it reacted with both, then it must be amphoteric. Alright, so a previous IG question was actually how do the type of oxides differ moving across the period. So basically, since I'm starting it off with metals and then non-metals, moving on from the left to the right-hand side, so the types of oxides range from basic oxides at the left, moving on to amphoteric in the middle, and then neutral acidic oxides, just like sulfur dioxide and so on. So basically, the transition is from basic to acidic, left to right. Now the fun part. What are salts? Which salts are soluble and not, and how do I prepare them in the lab? We've actually seen salts a while ago. A salt is actually formed from the reaction between acid and a base, or acid and a metal. So it has a cation part and an anion part, hence it's an ionic compound. And the naming is the first part usually comes from the metal or the base where it's coming from. So for instance, if I have potassium hydroxide and sulfuric acid, then my salt will basically be potassium sulfate. And of course, my second product in such case would be water. Right. How can I interpret this table? This is a very important table to memorize. Actually, you need to know which salts are soluble in water and which are not, because we're going to use it shortly. All sodium, potassium, ammonium salts are soluble. Try to use mnemonics to make you remember. So SPA or SPA salts are soluble. Similar to nitrates with ethanoate, they are all soluble in water. In case of chlorides, again, they're mostly soluble except for silver and lead. Hence, silver chloride is insoluble, similar to lead chloride. Likewise, sulfates are mostly soluble except for calcium, lead, and barium. So copper sulfate, for instance, would be soluble. Carbonates and hydroxides, on the other hand, are mostly insoluble except for group 1s, or the SPA we've just mentioned earlier, sodium, potassium, and ammonium. And calcium hydroxide, which is actually lime water, is slightly soluble. Now, how will I prepare a salt in the lab? The method I choose is going to depend on the salt solubility, which is why memorizing the table was very important. Now, if my salt was insoluble in water, let's say I was preparing barium sulfate or silver chloride, or in this example, I'm going to give you lead sulfate. The method I'm going to choose is precipitation. And you are asked to define a precipitate. A precipitate is actually an insoluble solid formed from the reaction between two soluble salts. So let's say I have lead 2 nitrate and potassium sulfate. Both are soluble because remember, all nitrates were soluble, all sulfates were soluble except for calcium, lead, and barium. When I mix them both together, let's follow now the steps. So basically in a beaker, you will add the mixture of both reactants together and stir. I will start observing a precipitate, which is insoluble lead 2 sulfate. How can I separate it from the mixture? The next step would be to filter it off, and definitely it's going to remain trapped on the filter paper as residue. What do we do to the residue? We wash with distilled water, then dry in the oven or between two filter papers. So the basic steps for the precipitation reaction to prepare insoluble salts are actually pretty easy. We mix together the two soluble salts in a beaker and stir. Then finally we filter, and the precipitate will remain trapped on the filter paper. We wash it with distilled water and dry. Now, what if the salt I was preparing was soluble? We have one of two methods. If it was a group 1 salt, like sodium, potassium, or ammonium salt, I'm going to use titration, because I'm preparing a soluble salt from a soluble base or an alkali. Whereas, if the salt I'm preparing does not include sodium, potassium, or ammonium, the cation part, therefore I'm going to use another method, which is basically reacting the acid with an excess of a solid metal or a base. Okay. Let's start with this method A. So this is the case of preparing a soluble salt, let's say copper sulfate. Again, all sulfates were soluble except for calcium, lead, and barium, so copper sulfate must be soluble. Now to prepare it, since it's a sulfate, therefore I need a sulfuric acid. And I need a source for the copper. In this case, I cannot add copper metal because we already know that copper is below hydrogen. Their activities here, so it's not going to react with the acids. So the only options I'm left with are either copper oxide or copper hydroxide or copper carbonate. Okay, what are the steps? I'm going to add to a beaker with sulfuric acid excess copper oxide. So we use a spatula, since this is a solid, to transfer excess copper oxide to the beaker containing sulfuric acid. Now, the common question, why am I using excess? To make sure that all the acid has reacted. Now, by the end of the reaction, I'm going to be left with the soluble salt form, but it's going to be dissolved in water, the copper sulfate. However, I will still see residue or a precipitate. Okay, what is this excess solid remaining? This is actually the excess unreacted copper oxide. And when you're asked to define the definition of excess, excess means more than needed to react. So how can I get rid of this excess solid? Simply, I'm going to filter first. So I got rid of the copper oxide as a residue. Now the salt, which I'm actually preparing, will be the filtrate. How will I obtain pure dry crystals of copper sulfate? I'm going to have to heat it till crystallization point. The crystals of copper sulfate will appear upon cooling. Now the final method to prepare the soluble salt of group 1 cation, okay, is titration. So in this case, all my samples are soluble, and this has to be done very accurately. Hence, we do not use a measuring cylinder for my measurements. I need to use burettes and pipette. So whenever I see this setup of a burette titrated against a certain liquid in a conical flask, this is the setup of titration. So, what do I need to know here? Now, firstly, you need to know the concept or the steps. Apologies. Alright, so basically I'm gonna add, let's say, the acid in the conical flask and the base in the burette, or vice versa. Okay? The base down and the acid up in the burette. Now, the sample added to the conical flask should be of a known sample. So let's say I should add 25 centimeter cube of sodium hydroxide onto the conical flask. What did I use to measure it? Since it's 25, pipette is okay, and of course burette will also be suitable. Right. I will then add the acid to the burette. It's going to be completely filled up to the 0 mark. I will start to open the tap or the stopcock. Type. When I open the tap, slowly the base will drop into my conical flask dropwise. Now, how will I know that the salt is formed? How will I know that I reached my end point? I should add an indicator with the flask before dropping my base from the burette. So this means, let's rewind the steps. I added sodium hydroxide base into the conical flask, but with the indicator. We cannot use universal indicator in titration because it will be difficult to determine the endpoint, and this is a common paper 6 question. Suitable ones would be phenolphthalein or methyl orange. So let's say I added phenolphthalein. Phenolphthalein is actually pink with alkalis. So since the alkali is down in contact with the phenolphthalein, so my starting color is the pink. Then I'm gonna place the acid in the burette, open the tap, drop wise, it's gonna fall into it. I'm gonna stop this or close the tap, turn it off when I reach the colorless color. So when the color of the indicator turns colorless. So now in the flask I have the sodium chloride solution prepared. What if I want a pure sample? Now, since I have the indicator mixed with my salt, then my only chance to obtain a pure sample is actually to repeat the experiment. Don't forget, once I reach the endpoint, I should record the actual volume of the liquid used to neutralize the other liquid in the flask. So for the pure sample, I need to repeat the steps using the same volumes and concentrations, but this time without the indicator. Finally, the salt I obtain, if I need it in the solid form, I'm gonna heat till I will take the filtrate, evaporate it till crystallization point. Crystals are gonna appear upon cooling. Now let's see a very interactive animation that's gonna help you understanding this better. Now, let's take the example of phenolphthalein, for instance. Now, we already know that if I'm placing a known sample of the acid in a conical flask, then I will fill the burette completely with sodium hydroxide till the 0 mark, and we added the indicator down with the acid. So at first, as you can see, the color was colorless, since phenolphthalein shows colorless with acids. What we're gonna do is we're gonna start adding the base. So as you can see, drops of sodium hydroxide are going down. Notice what's happening to the pH and the volume. Of course, the volume required to neutralize the acid now here is increasing, and the pH was initially acidic because the indicator, which is phenolphthalein, was in contact with the acids. I will keep on dropping my base until the first permanent color change. Now I stop, close the tap, turn it off, and record the volume required to neutralize. So if this was my 0 mark, and this is 18, so this means the amount of sodium hydroxide that has dropped is actually 18 millis. Record it in a table. Now let's repeat this, but this time with methyl orange. Now methyl orange, we said it's red in acids, orange in neutral, and yellow in alkalis. So again, I'm gonna add, so what's the expected color change? Basically, it's gonna turn into orange, a peachy color. Fine. Type. I'm gonna start adding the base. Again, the initial pH was actually 1 since HCl, most probably it was HCl, monoprotic acid is a strong acid. I'm gonna keep on adding until the first color change. Now if you pay attention, now I got the first color change. So remember this value, I needed 17 milliliter or centimeter cube of sodium hydroxide to completely neutralize this acid used. If you notice, if I keep on the tap flowing, if I keep on the liquid dropping, if I add more, it's gonna turn into yellow and the color is gonna keep on changing. However, is 21 millis the volume where I observed the first permanent color change? No. This is why whenever you get asked in paper 6 about the sources of error in titrations, it's that the student has overshot the endpoint, has gone past the endpoint, so this is an inaccurate result. What's an improvement to that? To repeat the experiment more than once and take the average. Alright, so remember I told you I used 17 milliliters of sodium hydroxide of a concentration 1 molars, which is 1 moles per decimeter cube, to neutralize my acid sample. Now, the tricky question is, what if I replaced my sample with a less concentrated one, half the concentration? So again, with the previous sample, it was of concentration 1 moles per decimeter cube, and I used around 17 millis to neutralize the acid. Now, if I use half the concentration, what volume do you expect to use? Now, let's see. So now I reached 7 millis, still no color change. I still have the same red color with the acid. Reached 17, nothing as well. 20s, 25. Now notice, this is the color change. I required around 33 or 34 milliliters. So this means double the volume, double the 17. Does this make sense to you? Again, let's recap. When I was using 1 moles per decimeter cube, I required 17 milliliters from this sample. But if I was using less concentrated sample, actually it was half the concentration, so this means it's going to be half as effective. So I need double the volume to neutralize the acid. Now, since I know this part is a bit tricky, I have a very nice analogy to help you remember. Now, so again, let's recap, but this time while changing their positions or their places of the acid and the base. This time I had my base was placed in the conical flask. It was sodium hydroxide mixed with phenolphthalein. Same sample, same concentration, same volume, same everything. يبقى أنا مثبتة لتحت. طيب. Now I have two different samples. I repeated the experiment with two different samples of hydrochloric acid. Apparently, one of them is more concentrated than the other. We need to identify which sample, A or B, was the more concentrated. Now, if you said A, you're correct. Why? Now, in order to neutralize the same sample of sodium hydroxide, since I needed less volume of sample A, so this makes it the more concentrated. If you're still confused, do not worry yet. Let's say instead of the sodium hydroxide اللي تحت دايما اعتبروه الستين. I have بقعة معينة وهشيلها ب a certain detergent, let's say Ariel. And I had two samples of Ariel. Obviously واحد فيهم more effective, more concentrated than the other. Which sample is more concentrated? لو عملت في experiment 1 استخدمت 15 millis of Ariel عشان أشيل البقعة دي. بس عشان أشيل نفس البقعة احتجت double the volume. احتجت كمية كبيرة قوي. So what does this mean? The more concentrated sample of Ariel, these labels are wrong by the way, okay, never mind these. So that alright, so this is one sample of Ariel and this is the other sample. Which sample was the more concentrated? It's actually the sample that I required less volume from it. So it is sample A. It makes sense. I have the same stain. I only used 15 millis to completely remove this stain. Whereas 30 millis of sample B. So أكيد sample B هو السامبل الدايلوت المخفف. طيب. What is scenario B بقى؟ أنا هنا كنت مثبتة مين؟ كنت مثبتة اللي تحت. اللي في الكونيكال فلاسك. المرة دي هثبت اللي فوق. أنا مستخدمة the same concentration of hydrochloric acid نفس السامبل في البيورات بس عندي two different samples of the bases. عايزة أعرف which is the more concentrated sample فيهم. Now sample A عشان يبقى completely neutralized وأوصل للend point it's required 15 milliliter but sample B required 30 milli, so this makes which sample more concentrated? Sample B, exactly. Again أنا كأني هنا أنا مثبتة المرة دي لفوق نفس الديترجنت بنفس الكونسنتريشن same Ariel بس عندي بقعتين مختلفتين. أكيد البقعة الأغمق هي اللي هتحتاج كمية أكتر من الديترجنت. I hope this is way clearer now. So in conclusion, for the different preparation of salts methods, the first question I need to ask myself هو السولت بتاعي soluble ولا لأ, which is why I need to memorize ال salt solubility rules. لو insoluble استخدم precipitation. Simply همix two soluble salts together to form my precipitate. I will filter it off, wash and dry the residue. بس if it's soluble هسأل نفسي هو does it contain sodium potassium ammonium ولا لأ. if it does contain يبقى استخدم titration and we just revise the steps. If it doesn't contain any of these group 1 cations or ammonium يبقى هستخدم ايه the other method, which is using acid with excess of a metal or excess of a base. بس في حالة acid plus metal, make sure that the metal is actually reactive with the acid. It should be above hydrogen to be able to replace it. Now the last chunk is all about testing, and again we've got lots of colors to memorize here, but the idea is very simple. Well, I do advise you to watch Cambridge videos for that. اللي هم حاطينها على Resource Plus. And there are pretty lots of other videos on YouTube, of course. طيب. So again, what is the concept here? I have a certain unknown sample. Let's say sample C in the lab. ومطلوب منك تعرف هو what is C? What is the identity of C? Potassium chloride, sodium sulfite, aluminum nitrate. مش عارفين. هنعمل ايه؟ هنعمل a series of tests. أي test بعمله يا إما هيديني a positive result يبقى هعرف إنه this is the actual cation or anion formed، أو هيديني negative result يبقى ده معناها إنه لأ this is not formed، يبقى هضطر أعمل other tests to see what is actually present. طيب regarding the cation part أنا عندي flame tests وعندي testing with sodium hydroxide and aqueous ammonia. Regarding the flame tests لو حتى سأل نفسه قبل كده هو ليه ال fireworks are actually made of colors, this is simply because different metal ions have different colored flames. When they burn, they give different colors. I need to memorize these 4 colors. Lithium is red, sodium yellow, potassium lilac, and copper blue green. And should also know out of the 2 marks how to conduct the flame test. Simply, you will dip the nichrome wire in concentrated acid followed by the sample of cations I'm testing, then expose it to flame. طيب, what if it's not one of these, or I didn't carry out a flame test? To identify the cation, I will either use sodium hydroxide or aqueous ammonia. طيب, لو حطيت to my unknown sample drops of sodium hydroxide وجالي white precipitate يبقى هشك في أول 3. Remember, ZAC the white, zinc, aluminum, calcium, their initials. طيب هفرق ما بينهم ازاي؟ هزود بقى كمية الصوديوم هيدروكسيد. في الأول أنا كنت حاطة drops بس، لو زودت ال precipitate فضلت شايفاه it's still clear, it's insoluble يبقى this is calcium. If it dissolved يبقى it's either aluminum or zinc. طيب وممكن repeat ال steps دي aqueous ammonia اللي هي ammonia water instead of the sodium hydroxide. Again, aluminum و zinc will give white precipitate بس calcium won't give me any precipitate. ولو ال white precipitate dissolved in excess يبقى ده أكيد zinc، يبقى أنا استبعدت aluminum. طيب نفس القصة بقى, this is simply memorization. Let's take another example. لو حطيت few drops of sodium hydroxide على my sample واداني green precipitate يبقى هبدأ eliminate كله وهشك في مين؟ chromium 3 و iron 2. هعرف منين which of them is present؟ هحط excess بقى sodium hydroxide بزيادة. والله لو داب يبقى this is definitely chromium 3. If not يبقى it's iron 2. And so on and so forth. This is important, guys. Ammonium ions for instance برضو هحط to my solution drops of sodium hydroxide وبسخن. المفروض إنه this is the reaction we've seen with the bases. فاكرين when we said a base plus ammonium salt will evolve ammonia gas؟ يبقى الجاز اللي هيطلع ده أولا ال observation بتاعته إنه هيحصل bubbles عنده pungent smell و when tested with damp red litmus paper it will turn blue. This is because ammonia is basic. Exactly. طيب. Now what about my anion part? We have specific tests and specific results for each test. So for instance, if I have a carbonate, it's known to react with acid to give off carbon dioxide. يبقى أحط لها acid وتست the gas given off هيحول اللime water milky وبشوف effervescence. طب لو عندي halide, chloride, bromide or iodide نفس التست بحط acidified silver nitrate. يعني ايه كلمة acidified silver nitrate؟ يعني أحط nitric acid الأول to remove any impurities عشان احنا عارفين انه النيتريتس are soluble فهتدوب الحاجة followed by silver nitrate. لو اداني white precipitate of ايه؟ of silver chloride يبقى this is a chloride. لو اداني creamy precipitate this is silver bromide، يبقى عرفت انه في bromide عندي. لو yellow precipitate يبقى this is silver iodide. طيب ايه test for nitrate. Now pay attention here because a lot of students actually mix this up with the cation ammonium. ايه اللي بيحصل هنا؟ اللي بيحصل انه هو I was looking for the shapes anyways, never mind. Insert shapes. Okay. When I add sodium hydroxide to nitrate in the presence of aluminum foil. يبقى هنا ال keyword عندي is aluminum. I didn't see the aluminum foil part في test for the ammonium. يبقى this is the test for nitrate. وبرضو I warm it gently. برضو هتطلع لي ammonia gas، عشان كده ال students usually بتتلخبط. بس عرفنا دلوقتي keyword. لو لقيت aluminum foil يبقى ده test for nitrate and not ammonium اللي شفناه من شوية. This one. alright. يبقى بس الجاز هيطلع لي نفس الحاجة، هيقلب لي ال red litmus paper into blue. Then we have the test for sulfates and sulfite basic memorization. طيب برضو note إنه sulfate is tested with nitric acid followed by barium nitrate. The white precipitate اللي هيتكون ده this is actually barium sulfate. يبقى you should remember colors guys. Chemistry is all about colors and explosions كمان. طيب sulfite when warmed with any acid it will give off sulfur dioxide gas. Sulfur dioxide, how can I test it? بحط عليه acidified potassium manganate 7 هيقلب من purple into colors. طيب it's important برضو to emphasize the difference between colorless و clear. أنا لما أقول colorless ملوش لون، بس a clear solution أنا ممكن يبقى عندي clear blue solution أو clear orange solution. كلمة clear يعني it's see through transparent زي فكرة الwater كده. And finally we have the tests for gases. Okay, so simple memorization as well. Already we tackled the test for ammonia gas, sulfur dioxide with carbon dioxide. We're left with chlorine, which will bleach the litmus paper, and hydrogen and oxygen. The difference is hydrogen will cause a pop sound when exposed to a lighted splint, whereas oxygen will relight a glowing splint. Again, this is a common trap. عشان تحفظوها الأكسجين O يبقى tested with a glowing splint, whereas the hydrogen with an H is tested with a lighted splint. طيب I'm actually done with الشرح. However, I would like to share with you the solution for one typical question on how you get asked on this last chunk of topic 8. This is actually typically the third question in your paper 6 exam. So I have a mixture of two unknowns G and H وعايزة أعرف their identity. طيب في solid G قال لي when I carried out a flame test it gave me a lilac color, so now I can conclude that it is potassium. طيب when I dissolved the solid in water and started adding hydrochloric acid and then warmed, the gas given off was tested with aqueous potassium permanganate. يبقى هبدأ أشك إنه إيه I'm testing for sulfite ion. طيب طالما اداني positive result يبقى ده معناه sulfite ion is actually present. ومين الجاز اللي طالع هنا this is sulfur dioxide هو اللي قلب لي potassium permanganate from purple to colorless. So what's the gas produced? Sulfur dioxide. What's the identity? As we said it's potassium. This is potassium what? Potassium sulfite. الcation والanion part. Now the rest of the question. Now solid H, I know its identity. So this time he's going to ask you to write the observations. And لو عندي calcium nitrate solid. This actually has a white color. معظم non-transition metal compounds are white. عكس transition metal compounds, they form colored compounds because again بيسألوا كتير على their appearance أو color. لو دوبتها في شوية distilled water فعملت sample stock كده هو بس قسمته على 4 different test tubes. يا ترى ليه؟ This is simply عشان أعمل 4 different tests ما يأثروش على بعض. لو حطيت drops of aqueous sodium hydroxide يبقى هفتكر إيه؟ هفتكر this table. One of the very important tables to memorize. يبقى sodium hydroxide in presence of calcium, this is what I need to solve the previous question. يبقى المفروض هيديني white precipitate upon adding drops. Upon adding excess هقوله precipitate is insoluble, it persists. هفضل لسه شايفاه. مع excess no precipitate وهنا as well no change. طب the anion was a nitrate. What was the test for nitrate? بحط sodium hydroxide with aluminum foil and I warm it. The gas given off was tested. طيب this is out of 2 marks. ساعات بيبقى out of 3. يبقى ساعتها محتاجة أزود كمان إنه effervescence is formed. Or preferably إنه the gas has a pungent smell. طالما قالي the gas produced was tested, يبقى basically I should say it was tested with a damp red litmus paper and it turns blue. Right, so this is basically the end. I hope you guys benefited a lot, and as I told you, pass this on لحد حاسين إنه they're panicking أو هيستفاد from this. And if you have specific topics that you'd like me to revise, I'd be more than happy to help you out with that. Thank you, guys.